So in the last case, we're going to investigate what happens where we have one real and repeated eigenvalue. So you only have one eigenvalue in this situation. All right, so this is the last, and we have not seen this case yet. So if you went through with this matrix of coefficients A, so I'm going to start out with an example in this case, and then we'll get to the result and start to apply it to this example. If we did our normal process where we did A minus lambda times the identity for this matrix, you would end up with the matrix negative 3 minus lambda, 1, 0, negative 3 minus lambda, and then taking the determinant of that matrix, which we always do to find our eigenvalues, we would end up getting, after multiplying that out, lambda squared plus 6 lambda plus 9, which can be factored as lambda plus 3 squared. And therefore we only have one eigenvalue, and in this example it is negative 3. Now we can also go through and find a corresponding eigenvector, but it turns out there's only one eigenvector for this example corresponding to negative 3. Better said, there's only one line of eigenvectors corresponding to the eigenvalue negative 3. One particular eigenvalue that I've chose to just use is v here. I'm calling 2, 0. So it's true, we still can do the e to the lambda t times v to create a straight line solution, but we only have one straight line solution in this case. We can't build the general solution because we don't have two straight line solutions for this particular example. So we have to do something different. And we're going to use the following theorem, all right, which tells us how to build the general solution. All right, now this case is one that doesn't show up a ton, but one we need to be aware of, all right, where we have a single repeated eigenvalue, all right, and we're going to look at the theorem and then again pay attention to what the components of the solution look like. All right, so here's the theorem. We have a 2 by 2 system where we have our coefficient matrix, and that coefficient matrix A has a single repeated eigenvalue, which we're going to call lambda. Now we're going to assume we are given some initial condition vector, and we're just going to straight out write the solution down using this theorem. All right, notice what it's saying here. It's going to take this format where we have e to the lambda t, so that's showing up in there, but it's the first term in here is e to the lambda t times v sub 0. Just using a little bit different notation for this one, where what is v sub 0? I'd use v sub 0 to emphasize that it turns out that we're going to call v sub 0 the initial condition vector, whatever you're given in your initial value problem. Or if you're not given one, you could just leave it generic as x sub 0, y sub 0. And plus, now this is where there's something new comes in. We get t times e to the lambda t. In the previous cases, we only either had e to the lambda times t, e to the lambda t, or e to the at times cosine or sine of bt, or maybe some constant terms that we saw in case 3. Case 4, we're introducing the last type, which is going to be some solutions that are going to have polynomials. In this case, t is going to be our highest degree times e to a power. All right, and that's going to be part of our components. Now, what is this vector v1? v1 is determined by doing a minus lambda times the identity, where lambda is the single repeated eigenvalue, times the vector v1. All right, so again, you're given your initial condition vector, right? You plug that directly in. You determine the vector v1 by writing down the matrix a minus lambda times the identity and multiplying that by v0. All right, let's talk about some of the, and so this theorem makes it actually pretty easy to solve these types of systems. There's the formula right there. All right, now there's some consequences of this, and this is a little different than the method that we've gone through in some of our previous cases, but we have to have some kind of different method here because, as we illustrated above, there's only one straight line solution. We can't build it up using a linear combination of two because we can only find one straight line solution using our eigenvalue and eigenvector approach. All right, now a few consequences. This new vector v1 is, if it's non-zero, then that vector will be an eigenvector. All right, that's resulting from the fact that that matrix A minus lambda times the identity is what's called a nilpotent matrix, because if you square that matrix, multiply it by itself, you get the matrix with zeros in every component, and that in turn leads to showing that V1 is an eigenvector to the eigenvalue lambda. All right. Now, if that's the case, our component functions, notice what they're going to take the form of. They're going to have e to the lambda t's inside there, and they're going to have t times e to the lambda t's inside there. The other possibility is that vector v1 turns out to be 0. This does not happen very often. This is a very degenerate case, in which case every non-zero vector would be an eigenvector to the system, and every solution to the system lies on a straight line through the origin. All right, that doesn't happen too often, but notice that the components of a solution in this case are only going to involve, in this case, e to the lambda t, right, not t times that. All right, once again, the long-run behavior, the limit's going to be determined by the eigenvalue. So in this case, it's determined by the eigenvalue lambda explicitly. Going back up here, e to the lambda t and t times e to the lambda t, they'll both approach 0 if lambda is negative. They will go to infinity if lambda is positive. All right, so the sign of the eigenvalue will determine the limit in this case. Now, one thing that's different about this, and I've highlighted in the last bullet before we go back to the example, we're not seeing any k1 or k2. In the previous cases, we used k1 and k2 as general constants. Then we plugged in the initial condition to find k1 and k2. In this theorem, we are actually just plugging in the initial conditions immediately, and there's nothing to solve for. So in that sense, it's somewhat simpler. All right, let's go through the process. All right, so in our example, our initial condition, let's go back up to that briefly here, for the example we started with was 1, 2. All right, so that's what the vector v sub 0 is going to be. It's going to be the vector 1, 2. All right, the system, keep in mind, was this. It was x prime equals negative 3x plus y, and y prime equaled negative 3y by itself there. All right, so let's go through and build up the solution. Again, remember, the solution in this case was e to the lambda t times v sub 0 plus t times e to the lambda t times v1, where we know what the vector v sub 0 is. It's just 1, 2. For us, in this example, we're working on lambda. The only eigenvalue is negative 3, so we're going to have e to the negative 3t's coming in both those places. The rest of the thing we need to figure out is this vector v1. All right, so to do that, remember v1 is defined to be equal to a minus lambda times the identity matrix times the vector v sub 0, which is the initial condition vector. Now, let's write out that matrix. All right, so our matrix of coefficients A was negative 3, 1, 0, negative 3. All right, so when we go to do a minus lambda times the identity, it's going to be minus negative 3 times the identity, which is going to be a plus, therefore, 3 times the identity matrix. All right, so now we're going to take our matrix, A. We're going to add on 3 times the identity, which gives us the matrix with 3's down the main diagonal and 0's in the off diagonal. And when we add those together, notice what happens. The diagonal terms add up to 0, actually, because we get negative 3 plus 3 in both cases. 1 plus 0 is going to give us a 1 here, and we get 0 plus 0 down below there. All right, so we have to figure out what that matrix is. And now we're in position to go through and find V1. All right, so what is V1? V1, remember, is A plus, or A minus lambda times the identity. We just figured that out. So for us, it is the matrix 0, 1, 0, 0 times our initial condition vector, which is the vector 1, 2. Okay, and just to recap, remember how we a lot of times do this multiplication. We write the left matrix down, the right product matrix above and to the right of that, and then what fits in the gap here is our corresponding product matrix. And if we do this matrix multiplication, first row times that column vector is going to be 0 times 1 plus 1 times 2, which is 2, and then 0 times 1 plus 0 times 2 is 0. All right, so that's in green there. Our vector v1 is 2, 0. If you go back to the beginning part of the video, I mentioned before that the vector 2, 0 is an eigenvector of this matrix. Alright, so what is the solution to this system? What is y of t? It is e to the lambda t, right? I'll just write the whole formula out again. Times v0 plus t e to the lambda t times the vector v1. And we found all of these things. Alright, again, we had to determine what the eigenvalue was. It was -3. The initial condition is what the vector v0 is, so it's going to be 1, 2. Plus, it's going to be t times e to the -3t times this vector v1, which we just figured out is 2, 0. Right, so there is the system. Notice there's no constants k1 and k2. They're completely found by using the result of the theorem. The last thing I want to do here before we look at the graph is, I don't actually have the graph for this one, but we could plot that in Maple. The last thing I want to do for this one is to distribute the scalar functions into the matrix, into the vectors, right, and then add them up. Right, so what we get here, if we did that, we get e to the -3t, and then 2 e to the -3t for the first one, plus the second one. Well, the second component is 0, so we multiply it by anything, it's going to be 0, and we're going to get 2t e to the -3t there. Alright, so combining them together into one vector, if we add our first components, we're going to get e to the -3t plus 2t times e to the -3t, and we're just going to get 2 e to the -3t in the second component. Alright, and sometimes you're going to see it written like that. You might also factor that out, and we just do that. Sometimes you might see this written where you're factoring out the e to the -3t from both of those terms, so you don't have to write it once, and what will we be multiplying that by? We'll be multiplying it by 1 plus 2t for the first component, and then we would just have 2 times e to the -3t there in the second component. You might see that done sometimes. Alright, so you get polynomials, in this case a linear polynomial, times e to the -3t. So that's it, and that's an example of how to solve a system, a linear system with a repeated eigenvalue. Okay, and so we'll just apply that theorem whenever we encounter that case. The thing I just wanted to really emphasize for this one is when you have a matrix or a linear system with a coefficient matrix that has a repeated eigenvalue, you're going to possibly end up with t times exponentials. T times exponential functions to be part of your components of your solution. Just a quick remark at the end. This is one way to cover this topic, and you might see in the textbook it talks about the matrix exponential toward the end. That would be an alternate way, and it's a nice way to do it for 2x2 linear systems. It turns out you can define the exponential of a matrix much like defining, or by using the power series expansion for E. So you might remember this formula from calculus 2, 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed. That's the power series expansion for the function e to the x that we're used to from calculus. Well, it turns out if you plug in a square matrix, M, you can define what's called a matrix exponential, and it turns out that matrix will converge in every sense that you would like. That series will converge in every sense that you would need, and it turns out that the solution to any initial value problem for a linear system, linear homogeneous system, can actually be expressed in terms of the matrix exponential. Now, in general, for a coefficient matrix A, that's a hard thing to do, but in the case of a 2x2 matrix, it's actually pretty simple, because it can be shown that e to the at, the matrix exponential, will come out pretty simple as e to the lambda t times the identity matrix plus t times n, where n is this matrix A minus lambda times the identity. Turns out that's a nilpotent matrix, and you end up with a general solution, or a solution that takes this form. This is equivalent to what we have in the theorem up above.